Good afternoon. Welcome to the 8th week tutorial session of NPTEL course, Convective Heat Transfer. My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So in this week, we will move to the internal natural convection. In the previous week, we have stopped till the external forced convection. External natural convection, and a few problems on the forced forced convection. So there was a doubt in the previous session that I tried to clarify regarding the integral solution of the momentum equation. So in this week, we'll move to the internal natural convection and discuss a few theoretical problems based on the different heat regimes of internal natural convection. Without wasting much time, we can move to the problems. This is the first question. Try to solve it. Meanwhile, I'll also discuss this within another couple of minutes. So we can move to the problem. So the question says, Employing the proper scales for the development of a thermal boundary layer along the heated vertical walls of a rectangular enclosure show that the momentum equation is dominated by the three terms of the scales which are listed: V by delta T, nu into nu by delta T cube, directly that is of the order of G beta delta T divided by delta T. That is the thermal boundary layer thickness. So first of all, we have to make sure that the pressure is eliminated from both the equations. So this is natural convection within a confined space. So that's why it's called an internal natural convection. It's a rectangular enclosure basically. So this pressure can be a potential threat to arrive at the final solution. So what we do is that we differentiate the x momentum equation with y and y momentum equation with respect to x, and then eliminate the pressure out of both of them. So what we could write is that we could write the equation to govern basic governing equations. So the continuity equation will be represented as dou u by dou x plus dou v by dou y equal to 0. Then the x momentum equation will be represented as dou u by dou t plus, it's an unsteady case, right? So dou u by dou x plus v dou u by dou y is equal to minus of 1 by rho dou p by so I beg your pardon, this is v by delta t and this is new v by delta t. That's a small correction in the question. Yeah. So minus 1 by rho dou p by dou x, that is a pressure term, and this corresponds to the unsteady term, and this is the convection term or the inertia related force. So this is pressure, and then there is this viscosity induced effect in the x direction. So what we assume is that x is the horizontal direction and y is the vertical direction. So the gravity acts in the negative g direction. So the presence of the buoyancy forces will be only in the y momentum equation. So that is the basic difference of this compared to the force convection in a vertical channel. And the y momentum equation will be dou v plus dou t u dou v by dou x plus v dou v by dou y is equal to minus of 1 by rho dou p by dou y plus nu dou square v by dou x square plus dou square v by dou y square. The same convection terms, unsteady term, pressure term, the viscous term, viscous forces, and then comes the term due to the natural convection. So it will be and the weight body forces will be combined together. Natural convection buoyancy forces and the weight will be acting in the opposite direction. So you have to represent both of them simultaneously. So you can write it as minus of g into 1 minus beta t minus t0. The weight acts in the negative y direction and the buoyancy acts in the positive y direction, and the opposite to the weight. And then the temperature equation. So the issue with these kind of equations is that the temperature and the momentum, both of them will be coupled. So the energy equation will be dou t by dou t plus u dou t by dou x plus v dou t by dou y is equal to alpha dou square t divided by dou x square plus dou square t divided by dou y square. So just like the previous case, this is the energy due to the convection. This is the diffusion term, and then there is this unsteady term. that comes into picture. So what we could do is that we could eliminate we could try to eliminate the pressure term from x and y. So what we can, before that we can enumerate these equations. There are 4 equations and we number them 1, 2, 3, 4. So in order to eliminate the pressure terms from 2 and 3, so what we do is that we differentiate to with respect to x and 3 with respect to 2 with respect to y and 3 with respect to x. So we'll get dou by dou y of dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to dou by dou y of minus 1 by rho dou p by dou x plus dou by dou y of mu dou square u divided by dou x square plus dou square u divided by dou s square. And when we differentiate the third equation by x, it will become dou by dou x of dou v by dou t plus u dou v by dou x plus v dou v by dou y equal to 1 dou by dou x of minus 1 by rho dou p by dou y plus dou by dou y of mu dou square v by dou x square plus dou square v by dou y square minus of dou by dou x of taking the negative outside, it will be the same term g into 1 minus beta into t minus t0. There's no sufficient space, that's why I have written it at the bottom. So what we could do, we can try to eliminate. So this will become, take the row outside, it will become dou by dou y of dou by dou y of dou p by dou x, it will be same as a dou by dou x of dou p by dou y. So in order to cancel out each other, we can subtract 2 from 3 and we can write it as, then the remaining terms will become dou by dou x of dou v by dou t plus mu dou v by dou x plus v dou v by dou y minus dou by dou y of dou u by dou t plus u dou u by dou x plus v dou u by dou y equal to, the new term comes outside, so dou by dou x, dou squared v by dou x squared plus dou squared v by dou y squared minus of dou by dou y dou squared u by dou x squared plus dou square u divided by dou y squared, and the one is a constant, so that will get eliminated, will become g beta plus g beta dou t by dou x. So we can denote it by 5. So this is the equation that we can get by combining x and y in a different manner, differentiating x momentum equation with respect to y and y momentum with respect to x, and we try to eliminate pressure out of it. But even then, So there are three unknowns, U, V, and temperature, and we have only two equations. So what we could try to do is that we can use scaling analysis to determine which of the terms in the momentum equation will be dominating, whether it is the conversion term or the diffusion term or the uh, buoyancy term. So basically, this has got uh, inertia term on the left hand side, the new viscous term on the the first term on the right hand side, and the buoyancy term on the furthermost right. So what we could do, we can take the LHS part. We have to do some kind of scaling in this kind of analysis. So LHS will be dou by dou x, dou v by dou t, plus u, dou v by dou x, plus v, dou v by dou y, minus of dou by dou y, dou u by dou t, plus u, dou u by dou x, plus v, dou u by dou y. So we have to literally use the scaling here. So how will we arrive at the scaling is the important concern as of now we have. So we could see v by t can be scaled as dou v by dou t could be scaled as v by t. This could be scaled as u v by x can be scaled as delta t. So in this case, what we assume is that it's a rectangular enclosure, horizontal walls are adiabatic, these two walls are adiabatic, and the temperature is on both the surface. So if at all the boundary layer will be formed, that will be with respect to the vertical walls, and there will be circulation. Since it's a confined surface, it's a confined enclosure, it will be having circulation depending upon the length ratio of the horizontal and the vertical dimensions. So if it is L and this is H, the X direction will not be scaled with respect to L, but rather it will be scaled with respect to the delta T, that is a boundary layer, because farther away from the surface, there will be core region that will not be interacting with any of these heat transfer that occurs due to the vertical warp. So we have to actually scale it accordingly. So X can be scaled according to delta T. So here also delta T, V will be scaled V into, this will be V squared, and Y will be scaled according to H. So it's a height of the plate or the enclosure. So we assume that it's infinitely it. So this is a cross section in the vertical plane. It will be, so this is the scaling of this one, and regarding Y, it will be 1 by H U by T, and this will be scaled as U square divided by delta T, and this will be scaled as VU divided by H. So basically, we have U, V as the unknowns, but we also have the continuity equation from where we can get a relationship between U and V. But it's better if you represent either in terms of U or in terms of V. We can represent here in terms of V because that is the vertical direction velocity that will be dominant for the natural convection circulation. So we can denote 8 by 6 from the continuity equation. We can write dou u by dou x plus dou v by dou y equal to 0. So it can be scaled as u by delta t is of the order of v by h. Therefore, u is of the order of v delta t divided by h. Substitute 7 in 6. We can write 1 by delta t v by t. We'll take the delta t inside. That will be better right now. V by delta T into T, UV, you can be written as V delta T divided by H. So, and then delta T gets cancelled out each other. So it will become H delta T, and then V squared divided by H delta T. So the order of, and this will be V delta T. You can be written as V delta T divided by H. So it will be H squared T, and then V squared delta T. U squared to be written as V squared delta T squared divided by H squared. So it will be H cube, and then V squared delta T divided by H cube. So what we could say is that for the boundary layer theory to be applicable, the size of the boundary layer should be very much less than the dimension of the plate. So by that logic, what we could write is that this H is significantly higher compared to these two. So what we could write is that since this is higher, so basically if you compare this and this, V squared take it out, there will be H delta T and there will be H cube by delta T. So this H cube by delta T will be significantly higher compared to the H delta T. But since this is a numerator, this will be very small. Similar to that, this also is very small. So we can neglect these two. We can neglect these with respect to these two terms. So these two terms will be eliminated, and then so basically this term will be V delta T divided by H squared. The H squared is quite large, and therefore this term will be small. So we can neglect these with respect to this two. So what it means is that with respect to what it means is that the second time the x dimension, uh, the x dimension momentum equation is that the inertial terms of the x dimension momentum equations are very much less compared to that of the y dimension momentum terms. So basically we can eliminate the second part of the left hand side. So that will be one simplification. So it will be remaining terms will be V by T delta T, V squared H delta T, and V squared by H delta T. So now what we could do is that we can do scaling analysis for these three parts. This is the unsteady term. This is the conversion term. So out of this, which will be remaining? That is a question. V by T delta T. This is delta T. Then what we could try to do is that we multiply the terms with the T delta T divided by V. That will give us 1, and then it will be Vt divided by H, and both of them scale will be same. So what we could see is that Vt divided by H here, the case of natural conversion, the time step, that is very much less than 1. So that means that so this time steps tends to 0 as time to this particular term. These terms tends to 0. Therefore, the only term that remains is V by T delta T remains. So in the left hand side, only one term remains. That is the unsteady term of y momentum equation. and whose scale is V by T delta T. So basically this term, only this term remains. That is the pi momentum equations unsteady term. Now we'll move our attention to the focus to the second, the right hand side of the right hand side of the equation number 6, equation number 5. Right hand side of equation number 6. Now we can try to do the similar kind of scaling on the right hand side to arrive at the terms that will be remaining at the end of scaling analysis, the terms which are significant. So we have actually got an issue here because the what we did was that in the case of natural convection, since continuity equation is there, we have three equations. So we combined the x and y momentum equations to remove pressure. Therefore, we have UV and then there is temperature term as well. Continuity equation we can use straight away to have an equilibrium. So it's more like a check to ensure that we are the value we substitute in U in the combined momentum equation and the energy equation will be satisfying continuity. So basically that's the continuity equation. So RHS on the RHS of the equation 6 corresponds to this part. So that will be equal to nu into dou by dou x of dou squared v divided by dou x squared plus dou squared v divided by dou y squared minus of dou by dou y dou squared u divided by dou x squared plus dou squared u divided by dou y squared plus g beta delta t divided by delta x. So we will do the scaling analysis, similar kind of a scaling analysis here as well. So what we could do is that we will look for scaling. So it will be nu into x, it will be scaled as dou t into v divided by dou x squared. So this will be delta t squared v divided by x squared. This will be 1 by h u by delta t squared u by h squared. And this will be scaled as g beta delta t divided by delta t. So we can't actually ignore this part because it's a natural convection which is driven by the buoyancy. So this term will always remain. Will always remain in the solution. Yeah. Then the U uh, based on the continuity equation, U will be scaled as so this combines together. We can get it as mu v divided by delta t cube. So since h is very much larger than that of delta t, this will get eliminated because this term will be very less negligible compared to this term. Similarly, this is negligible compared to this one. So the only term that remains here is nu v divided by delta t, and here it will be u divided by h delta t squared. And then comes comparison between these two. U v, this is nu v, and this is also nu v, nu u h divided by delta t squared. So u could be written as nu v delta t divided by h. So that will be v delta t divided by h. Nu v delta t gets cancelled, h squared delta t. So we could see that the numerators are same and denominators which are sort h squared, and which is quite big compared to delta t squared. So this is negligible compared to this is negligible compared to this. So this term remains and this term remains from the pure scaling analysis. So we can denote it by 9. So basically three terms remains. That is, this is the in the y momentum equation, this is the unsteady term, and in the y momentum equation, the diffusion term dou squared v divided by dou x squared. So basically this term remains and this term remains, and the convection term remains. So the u terms, the differentials of u terms gets cancelled out each other, and then the x momentum equation completely is avoided. But it's not avoided as such, because in order to calculate the pressure, you need x momentum equation as well uh, in order to back substitute and find it out. So the terms remaining based on the scaling analysis are v by t delta, that is the unsteady term, inertia term, that is the inertia term, unsteady, and then mu v divided by delta t cube, that is the viscous force, viscous term, and then gp delta t divided by delta t, that is the buoyancy term. So this validates our claims that these three terms are the dominating terms uh, in the set of xy momentum equation and continuity equation, xy momentum equation basically. That solves the first problem, where we were supposed to find so which terms out of the general x and xy momentum equations dominates the proceedings. So we found out that the inertia term of y momentum equation, unsteady inertia term of the y momentum equation, the viscous term of v with respect to x, then the buoyancy term of the y momentum equation. These three dominates based on a scaling analysis. So we had employed continuity equation, x momentum and y momentum. We didn't use energy equation, I just wrote it down so to show that that sets completes the equation. So if you want to solve, because the temperature, temperature is an implicit equation, so you can explicitly find out the temperature once you find out the velocity from here. So the both the are the both the momentum equation and the energy equations are interdependent in this case. Okay, that finishes the first question, and we can move into the second problem. The question says rely on pure scaling arguments to prove that Rayleigh number with respect to height h is less than 1 denotes the domain in which the overall heat transfer rate across a square enclosure is dominated by pure conduction. So this is the first regime of the first heat transfer regime. So we have to say that Rayleigh number less than 1 denotes the phase where the heat transfer ratio across a square enclosure is dominated by pure conduction. So for other cases, for a shallow enclosure, for a slender enclosure, and one where the Rayleigh number is very much high, it will be having a much higher natural convection. But if it is conduction, pure conduction, there will be a small circulation, but that doesn't participate in heat transfer. So we have to check. We have to just do the scaling analysis to prove this point. Try to solve it. I can attempt it after a couple of minutes. So we can look into the second problem. So this is the case of a rectangular, a square enclosure. Sorry, it's a square enclosure with heat transfer rate across. So the horizontal walls, the horizontal sides of these enclosures will be adiabatic, and heat transfer happens from uh, from the vertical one wall to the other wall, where the temperature different, where the temperature drop is delta T. And in this case, we have to see when the Rayleigh number is less than one, it's a convection, it's a conduction that dominates, and the convection, the heat transfer due to convection, natural convection, is minimal. So, so we can denote the energy equation. So that will be steady terms only, u dot t by dou x plus v dot t by dou y is equal to alpha dou square t divided by dou x squared plus dou square t divided by dou y square. This is the convection term and this is the conduction. So based on the scaling analysis, what we could do is that we can, before that we can denote the enclosure. We can draw the enclosure. So this will be the height h, and this will be it's a square enclosure, so it will, this dimension will also be x. So this will be adiabatic wall and this will be adiabatic wall, and the temperature drop across this direction delta T. And we need to prove that only conduction remains when the conduction, that is this particular term, remains when the Rayleigh number is very much less than. So before that we can scale it accordingly. So this could be scaled as the, basically the scales of these two should be the same. So this could be scaled as, convection term could be scaled as V into so basically G happens in this direction, and this is the Y direction and this is the X direction. So this could be V delta divided by Y could be H, and the conduction term could be scaled as alpha delta T divided by X squared. So the given condition in the problem is that it's pure conduction that happens between the left wall and the right wall. So we need to prove that this happens when the Rayleigh number is very much less than one. With Rayleigh number with respect to height F or the width h is very much less than one. So what we could do is that this v delta t divided by h is less than this particular term. This is given in the problem. Given conduction dominates convection. So what we could write is that v delta t divided by h is very much less than alpha delta t divided by h squared. But then in this case, v is an unknown. This scale is an unknown factor. Delta t could be written as delta t itself, and h is unknown. So v is an unknown basically. So we have to find, somehow we have to convert that v into some other terms. Then we can reduce these terms on the left and right hand terms in terms of Rayleigh number. So if we can write v in terms of some other forms, we can actually arrive at this Rayleigh number. So basically Rayleigh number will be having g v det. G is the equation of it's basically Grashof number into Prandtl number. No? So for that will be g beta into delta t h cube divided by nu into alpha. That will be the equation. So in that case, there is some terms related to g gravitational force beta. So basically buoyancy term. and there is no term corresponding to the velocity. So if we can denote this velocity scale in terms of g beta delta, we can represent this equation in somehow in the form of a Rayleigh number. So for that, we need to make use of the momentum equation. The Y momentum equation. In that, we need to use the balance using the scaling analysis. So in the previous case, in the previous question, what we would see is that from X, Y momentum equation or continuity equation, we have arrived at the scaling analysis. From the scaling analysis, the terms which dominates on the left and right hand sides. From the previous question, we already know that the inertia terms mu v by delta t cube could be scaled according to the buoyancy term. So the viscosity term, viscous term is approximately buoyancy term scaled accordingly, scaled approximate to the buoyancy term. So G b delta, it's not delta t cube, it's delta t. So from this, what we could write is V could be scaled as G beta delta t divided by nu into G beta delta t squared divided by nu. So that can be the second equation. So substitute 2 in 1. We'll get so on the left and right, we'll cancel out a few terms. Cancel out. So that will be equal to G beta delta t I beg your pardon. There's a small correction. So in the previous case, we had scaled the bottom terms in terms of delta t cube, both of them. But in this case, since this is a pure conduction case, the dimension can be scaled according to the full length because there is no convection as such. So the scaling terms on this term on the denominators will be with respect to h. So that was actual reason why we were not getting the answer. So it will be since this is a pure conduction that happens from this side to this side, the entire length of the plate, entire length of the enclosure in the horizontal dimension will take part. So the scaling should be done with respect to h. There is no boundary layer as such because here it's a conduction that dominates. So it will be h cube and h. So basically this will be h squared, and that solves the problem. So this will not be delta t squared. This will be h squared, and this will be h cube, and this is less than this one. So this will be h cube should be less than 1. So this will be Rayleigh number. This is a formula of Rayleigh number. So Rayleigh number with respect to h should be less than 1 for the heat transfer within the enclosure to be uh, dominated by your conduction. So in this problem, what we did was that we had the energy equation, and we have using the basis scaling analysis, we have seen that the convection will be less than conduction that is given in the problem, but we do not know the scale of velocity. So that velocity scale we will try to attain from the previous question that we have seen. We have seen that among the conversion term, this will be the term that dominates, and among the buoyancy term, and it will be of the order of the buoyancy term. And here, since this is pure conduction, it should be scaled with respect to h rather than delta t. So that will come into picture, and then we'll get a scale for velocity, and we substitute and find that the conversion term is less than conduction. So that means that this happens only when the dimensionless parameter of Rayleigh number is very much less than 1. So this means that that there will not be conduction at all. There will not be uh, any convection at all. It will be pure conduction. And if you could closely observe, if you take a square enclosure, circulation might be there, but that due to the stratification, but it doesn't actually convert into a it doesn't actually convert into heat transfer due to natural convection. So this doesn't take part. This does not take part in the natural convection take in the natural convection heat transfer. So that completes the second problem. Now we can look at the third problem. So this is a theoretical question. So we have to describe the different heat transfer regimes in internal convection. So basically, we have to describe which all are the heat transfer regimes in internal convection, and at what particular condition they occur, and draw the schematic of the natural convection flow. So in the case of natural convection, so if you consider an enclosure and these surface are adiabatic horizontal surface and vertical walls will be having some heat that will be transferred to the opposite vertical wall. So this will be at one temperature T1 and this will be at another temperature T2 and there will be delta Q equals. So the convection term could be scaled as MCP delta T enthalpy. The left hand side term could be scaled according to the velocity. The flow rate with for a unit length per unit length it could be scaled as rho velocity and the C and this will be the vertical dimensions. So that will be delta T. That is the boundary layer thickness. And then C into delta T. So this could be scaled as K into delta T divided by so this is flow rate per unit length. So this is the heat transfer rate per unit length. So this is equal to K into delta T uh, into Rayleigh number raised to minus raised to 1 by 4. So we can actually reduce this into this form. So what we could do is that this is for convection term and for the similarly we can write it for the conduction as well. Sorry for the disruption. So yeah, for the convection, this would be written as this, and then for the pure conduction case, what we could write it as Q dash conduction from the top to bottom. Left to right conduction from top to bottom is directly proportional to K L delta T divided by H. This is H, this is L. So when the convection dominates for the heat transfer from the from left to right, the conduction from top to bottom, from top to bottom should be minimal. So that means that KL divided by delta H by H should be less than K delta T RH raised to 1 by 4. That implies H by L should be greater than Rayleigh number raised to minus 1 by 4. So that will be the particular ratio that we'll be having. So based on the slenderness ratio of H by L, we can divide the domain particularly. So when the KL delta T divided by H less than this one, so conversion dominates, but the other the opposing case, when the conduction dominates over the convection, so the Rayleigh number should be less than. So what happens is that the Rayleigh number uh, raised to 1 by 4 should be less than 1 in that case. That will be the first case. So that is one side. So we can denote particular geometry based on this H by L ratio, and we can then demarcate clear cut divisions between these sub branches of this uh, convection regimes, heat transfer regimes. So what we could do right now is that we know H by L ratio should be greater than Rayleigh number raised to minus 1 by 4 for convection to occur. The only case where it doesn't occur is the when the Rayleigh number raised to 1 by 4 less than 1, it's pure conduction that dominates, pure conduction. So that will be the regime 1. So this is when the temperature varies linearly across the cavity. Hence, heat transfer between the two sidewalls is of the order of K into H into delta T divided by L. So this is K into H into delta T divided by L. So it happens between left to right in this direction. So that will be the first regime when the heat transfer from the left to right will be K into area, it will be H into 1 into delta T divided by L. So in this case of the conduction, we have denoted it as the conduction from the top to bottom. So in this case, your conduction, so it will be denoted as K into, from the left to right, it will be K into H into delta T divided by L. The horizontal temperature gradient will be delta T divided by L. So if this is the L and this is the H, so this regime, there could be some circulation, but that doesn't add that doesn't add it to the total heat transfer. So the heat transfer happens from left to right. So pure conduction case that we have seen in the second question. So this temperature gradient due to the conduction will actually result in a slight circulation, but this heat transfer this heat transfer contribution from this circulation is very negligible. So what we could see is that so the conduction happens in this direction, but there will be gradient in this direction as well. So based on that temperature difference, there will be small circulation, but that contribution is very negligible. So that is the pure conduction regime. That is the regime 1. Then regime 2 is called a toll enclosure limit. So that means that H is very much greater than that of L. So what happens is that when H is very much greater than L, uh, Rayleigh number will be very much greater than 1. Sorry, a Rayleigh number will be very much less than 1. Rayleigh number. So 1 by Rayleigh number will be very much less than. So H by L, this particular quantity will be very high. H by L will be very high. That means that this quantity will be very less. So in this case, what happens is that H is very much greater than L. So what we could denote it is that this is a toll enclosure. This will be the H, and this is L. In that case, there will be a circulation like this. So for most of the enclosure height, the temperature varies linearly between the two side walls. The heat transfer rate is of the order of the same K H delta T divided by L. Just like the previous case, and the clockwise circulation is characterized by distinct layers in the vicinity of the top and bottom walls. So there will be clear-cut demarcation between the layers, between the top and the bottom walls. So regime 3 is I beg your pardon, in the previous regime 2, I told that this is a high Rayleigh number. That's not the case. This is a case where H is very much greater than L. That's it. The third case is the normal natural conversion rate and natural conversion regime when the Rayleigh number raised to Rayleigh number is very much greater than 1, high Rayleigh number value. So that means that that's called a boundary layer regime. So in this case, vertical thermal boundary layers form distinctly along the differentially heated side walls. The heat transfer rate across the cavity could be scaled as not the entire distance. So in the previous case of tall enclosure limit, we had actually scaled it based on H and L, but that's not the case here. There will be the formation of the boundary layer. So what we could see is that it will be of uh, so the heat transfer rate should be scaled for delta T. So the new scaling will be of this order. Uh, so in this case, what happens is that there will be a core region which will be unaffected by the heat transfer. So that will be the third regime. And then comes the fourth regime for the shallow enclosure limit. So in this case, what we could see is that it's a regime like this. So it's XL, sorry, XL. And in this case, rather than vertical boundary layer, there will be formation of the horizontal boundary layer. So I beg your pardon. So in this previous case, it was a horizontal boundary layer, and here in this case, there will be vertical boundary layer. So formation of vertical boundary layer and could be scaled as K vertical boundary layer. So boundary layer originates from the horizontal surface. So could be scaled as K into delta T into delta temperature divided by uh, but there's a small correction. So I'll use the next page to write it. It's a bit of confusion. So fourth regime is the shallow enclosure limit. So so for the conversion to dominate, there should be the condition that H by L should be very much greater than Rayleigh number raised to minus 1 by 4. So that is given for the fields of 2, 3, and 4. But what now we are looking is just the variation in the uh, variation in the geometry. So in the case of shallow enclosure, so length height will be that the boundary layer formation will be like this. So there will be the formation of vertical boundary layer, not the horizontal boundary layer that we have seen in the case of uh, in the case of the second, that tall enclosure. Here there will be the formation of the vertical boundary layer. So, and the scaling of heat transfer rate will be again of the same order. So K into H delta T divided by delta TF. So this is the case for the shallow enclosures. The scaling will be almost the same, but what happens is that the scale represents an upper bound because an additional insulation effect is provided by the long horizontal core of the cavity. So there will be a core region which doesn't participate in the heat transfer due to the natural conversion, which will be at the initial temperature. So whatever the heat transfer that might occur, that will be scaled based on the boundary layer thickness delta T. In this region, in the core region, the two branches of the uh, counter flow make good thermal contact. rendering the counterflow and effective insulation in the left to right direction. So as and when the fluid gets heated up, it moves towards the colder plate and then comes back, but the inner region of the core will remain unaffected by this flow. So that completes the third question where we had actually derived. So this in the previous question, what we have seen is that Rayleigh number with respect to x should be less than 1, in which the overall heat transfer rate across a square channel is dominated by the pure conduction. So conduction dominates from the left to right. So that's what we have seen, and we have shown that Rayleigh number will be greater than 1. But in the case of uh, in the case of uh, when we try to extrapolate the same analysis to the internal natural convection regimes to discuss the cases of different regimes of internal natural convection. We had to actually go from the basics where we have denoted the heat transfer from the top to bottom, and we have tried to scale it down in terms of conduction. So if the heat transfer has to happen from the left to right, the conduction part in the vertical direction should be very minimal. So based on that, what we have attained is that h by l should be greater than Rayleigh number raised to -1/4. That is one particular fixed basic basis on which the convection happens. So if that condition is not satisfied, that will be pure conduction. That is the regime one, where the scaling will be done based on the total length of the total length of the plate, horizontal dimension, rather than the boundary layer thickness. In the case of toll enclosure, the same happens. The with respect to L, it will happen. So this in this case of a toll enclosure, the formation of the boundary layer, it should be a tall enclosure. That means that height is very much greater than that of the horizontal dimension L. So in that case, it has to be scaled with respect to L, and the boundary layer might not be fully developed. And the third regime is the higher Rayleigh number value. So in that case, it has to be the dimensions, the boundary layer dimension has to be taken into account rather than the full dimension of the plate, delta T. And in the fourth case, shallow enclosure limit, the same like the previous case, the full dimension may not be required. It's delta T that needs to be accounted. The boundary layer thickness needs to be taken into account here. So regime 3 and 4 are kind of similar, but regime 1 and 2, the heat transfer rate scaling will be kind of same. So that completes the fourth question, and we can actually move into the fifth one. So looking at the problem, this is a question on natural conversion. I'll read out the problem. The large diameter cylindrical reservoir shown in the figure is perfectly insulated and filled with water. Two horizontal tubes with an outer diameter of 4 centimeters are positioned at the same level in the vicinity of the reservoir center line. The temperatures of the tube walls are maintained at T1 equal to 30 degrees Celsius and T2 is equal to 20 degrees Celsius by internal water streams of control temperature, appropriately control temperature. Calculate the heat transfer rate from the hot tube to the cold tube via the water reservoir by assuming that tube to tube spacing is wide enough so that the boundary layers that coat the tubes do not touch. So this is a case of natural convection. Gravity acts in the downward direction. It's an adiabatic surface, an enclosed surface, and the diameter d of the tubes, and then the temperature. There will be the formation of the boundary layer in and around the temperatures, in and around the cylinders, but the distance is sufficiently large to prevent the boundary layers to touch. That prevents the boundary layer from touching each other. So we need to calculate the heat transfer rate from the hot tube to the cold tube via the water reservoir by assuming that the tube to tube spacing is wide enough. Look into the problem. I'll try to solve it within a couple of minutes. You haven't tried to solve it, I'll try to solve it. This is though it is though these two cylinders are fixed are horizontal cylinders fixed inside water reservoir, and there is an adiabatic outer cylinder. So the water is confined within the adiabatic surface, but the outer surface of these two internal uh, horizontal tubes are at temperatures T1 and T2, and the natural convection occurs on the outer surface. So even though this is a confined space, this is not a case of a flow internal natural convection, but rather it's an external natural convection. So that's a point of difference in this question. So what we could do is that once we got the basic concept, then it's straightforward. It's a straightforward resistance-based approach problem. So we can try to denote it straight away. So we need to calculate the heat transfer rate from the hot tube to the cold tube. So uh, if you denote, if you assume that the uh, these two tubes extends infinitely into the plane of the papers, we can actually assume unit length in that case. So the temperature gradient in that particular dimension will be negligible compared to the temperature gradient in the in this dimension from the first tube to the second tube with on the plane of the paper. So we can denote the heat transfer rate that happens from the first tube to the second tube. So using a resistance-based approach from the outer surface. So T1, and this is a boundary layer resistance that goes to the fluid at T infinity. And from there, similar resistance uh, is there from the fluid to the second tube outer surface as well. So this is a boundary layer resistance. The boundary layer resistance is basically could be represented in terms of heat transfer coefficient. So if you assume a unit length, it will be pi into d into 1. Similarly, on the other side, the heat transfer coefficient will be same h bar. That depends upon the Rayleigh number and the fluid properties, average fluid properties. So and pi into diameter remains the same into 1. So the properties to determine the heat transfer coefficient, basically Nusselt number, you require Rayleigh number. For that, the fluid properties needs to be measured at the average temperature. The hot reservoir will be at uh, T1 will be at 30 degrees Celsius. T2 will be equal to 20. Therefore, the water temperature, we can assume it to be T1 plus T2 divided by 2, normally just similar to the film temperature assumption. So we need to calculate the properties at 25 degrees Celsius, basically. The heat transfer rate could be written as basically a resistance-based approach T1 minus T2 divided by the summation of the series resistances R1 by R2. That is 1 by H into pi D1 plus H bar, same resistance, same dimension. It's the same resistance. So this is same. So it could be written as 2 by H into pi by so it will be H into pi D by 2 into T1 minus T2. So H into T could be written as Nusselt number into K. So Nusselt number, average Nusselt number into K into pi by 2 to T1 minus T2. This will be the heat transfer rate. So once we get to know the So I beg your pardon, there was a small correction. So the water temperature. Since this is a series-based approach, we can write. We can consider the water will be at a average temperature between the two reservoirs, since the resistances are same. So water will be at 25 degrees Celsius Celsius. Therefore, the properties needs to be calculated at the equivalent to the film temperature, that is uh, T1 plus T infinity by 2, that is 22.5 degrees Celsius. So the properties needs to be evaluated at this temperature. So there was a small correction from what I have mentioned in the previous discussion. So the properties needs to be calculated at this temperature, and then the temperature difference across the boundary layer will be 5 degrees Celsius, basically 30 minus 25. So what we could write at 22.5 degrees Celsius for water, K is equal to 0.6. Then the value of G beta divided by alpha nu will be equal to 19.8 into 10 cube divided by centimeter K, and the Prandtl number will be equal to 6.21. Therefore, in order to calculate the value of the heat transfer rate, you require a Nusselt number. Once you get the Nusselt number, you can get it straight away. So Nusselt number for the horizontal cylinder and external natural conversion can be given by the formula that was discussed in the previous. For the external natural conversion, so Nusselt number will be equal to 0.6 plus is 1 by 6, 1 plus 0.559 divided by Prandtl number 9 to 16, the whole power 8 by 27 is 0.559. This is 1 plus 0.559 divided by Prandtl number raised to 9 by 16 raised to 8 by 27, the whole raised to 2. So substitute for that we require the value of Nusselt Rayleigh number. So Rayleigh number we can calculate for this case. So Rayleigh number with respect to the dimension D is equal to G beta alpha nu into D cube into delta T. So Rayleigh number for this case delta T will be 5 degrees Celsius between the surface of the uh, tube as well as the water, which is at an average temperature between the two tubes, and the GBT alpha nu that we have calculated at the film temperature or the average temperature between the surface as well as the water based on the average boundary layer values. So it will be 19.81 into 10 cube into divided by centimeter cube Kelvin, and the diameter of these tubes will be at 4 centimeter cube into 5 degrees Celsius. So that would be 6.34 into 10 power 6. So this is laminar case. We substitute that into the Nusselt number. So therefore, 2 becomes Nusselt number D equal to substitute the value of the Prandtl number for 6.21, Rayleigh number 6.34 into 10 power 6. We'll get the value 30.45, and based on that, the heat transfer rate is equal to 5 by 2 into 0.6. That is the K for water at this temperature 22.5, 30.45. That is a Nusselt number value, and 30 minus 20 temperature difference between the first and the second tubes surfaces. So that is 10. So you get the value of the heat transfer rate is equal to 287 watt per meter. So this was slightly tricky question in the sense since we are discussing it in the internal free conversion case, we might think that this is a case of internal convection, but the surface, adiabatic surface is at the outside. But the tube surfaces, the inner tubes, the two tubes that are mentioned at T1 and T2 are at a different temperature. So basically, the natural convection occurs at the outer surfaces of this, and this is an external convection cases. So we can use a resistance-based approach to get the value of the heat transfer rate per unit length. So we can assume that it's unit length into the plane of the paper. And then for that, we require in order to calculate the heat transfer resistance, we require the heat transfer coefficient, and that you can obtain from the Nusselt number. So for the case of Nusselt number, we have to obtain the properties at uh, Nusselt number for the horizontal cylinders and external natural convection. We can use this formula. And for that, you require the Rayleigh number. Rayleigh number you have to actually calculate at the average temperature between the surface as well as the wall. And we in this case evaluate the temperatures at 22.5. It can be 27.5 as well, but these properties are almost same, so we can approximate this to be 22.5 and have determined the properties. And So basically, there is just 22.5, 27, and we calculate it at either of these temperatures, it won't be making much difference at all. So the approximate value of the Nusselt number will get as 30, and then the value of Nusselt number we get it as 30, and from that we can get the heat transfer rate to be 287 watt per meter. This is per unit length heat transfer rate. So that completes the session for today. In this week, we had seen a few particular problems on internal natural conversion. The first was a derivation problem for the scaling analysis for internal natural conversion. And we had assumed that based on the scaling, we have determined that these three terms, inertia term, unsteady inertia term, viscous term, and the buoyancy term are the significant ones for the internal natural conversion case, purely from the scaling analysis. The second one was a continuation of this one, where we have to see that in the case which is dominated by pure conduction from the left wall to the right wall, the condition will be given as Rayleigh number less than 1. So from the pure scaling analysis, we obtained the value from of the energy equation. We obtained that this is the condition that follows the loop. But in that case, the velocity is an unknown. So the velocity scaling we can obtain from the first question n. But the pure conduction happens. So the scaling of x should be based on h rather than delta t. So based on that, we get the Rayleigh number should be less than 1 for pure conduction to occur. And the third one is projecting this for third one is the discussion on the heat transfer regimes in internal conversion. So that the first one is pure conduction is kind of same, where the transfer rate will be scaled based on the total length L, just like the previous case. So it was a square enclosure, that's why we have taken H, but it's a rectangular dimension. So it will be this dimension for pure conduction. Thus, then we discussed up to the regime 2, which is a tall enclosure. Quite similar to this one. The heat transfer rate will also follow the same kind of uh, scaling analysis, scaling value. And then the third one is the case where the Rayleigh number is greater than, very much greater than 1. It's a pure natural conduction case where boundary layers will be formed. And then the fourth one is the case of the fourth one is the case of uh, shallow enclosure limit, where H will be very much less than L. In this particular case, what we could see is that uh, the heat transfer rate will be following the same suit as such. There will be the formation of boundary layer, and that will be the steering limit of the X dimension where the heat transfer happens. So that will be the four regimes of the heat transfer. And in the fourth problem, it's a problem on external natural convection for a two tubes dipped inside a water reservoir within an adiabatic enclosure. So the heat transfer rate will be decided by the Nusselt number values of the external natural convection for horizontal cylinders. So once we get that logic, it's quite straightforward. That completes the session for today. If you have any doubts, you can post in the course website. There's a forum available in the course website, so you could post those queries there, and we'll try to respond immediately. If any other queries are there, you can actually discuss in the next week's lectures. Uh, that's all for this. We'll meet again in the next week with the continuation of internal natural convection. Thank you.